This is the final design presentation by Group 729G. Problem definition. The aim of our project is to create a solar panel system that maximizes energy production for our client, the Queen Solar Design Team. The client's needs include to have a roof shape that is efficient, an efficient solar array, a battery system that fits within 64 meters squared, and one that is affordable. Other than the client, other stakeholders include customers, manufacturers, environmental maintenance workers, as well as the municipal government. Other important factors include the environmental regulations and the engineering code of ethics. Our team proposes the final project to be presented to the client via solar array design represented by a CAD model to show the array configuration, as well as being supported by both a financial analysis and an energy analysis. Financial report showing the payback period and the return on investment, and an energy analysis showing the varying outputs of designs and demonstrating the reasoning behind the team's final decision.
This is the research summary. Here we'll be covering a brief overview of the main components of the project as a precursor to the more in-depth analysis to follow. When researching the roof's design, it was important to compare different roof structures and angles with the aim of maximizing exposure to the sun. It was also very important to consider roof materials for eco-friendliness, cost, insulation, and total energy usage. While researching the solar array, we looked at the panels, installation, and wiring. For the panels, we considered benefits in cost versus efficiency and in the number of panels needed for our desired output. When considering installation, we looked at the cost and different methods of installation, thinking particularly about panel angles for sun exposure. Though wiring seems small, it is a crucially necessary part of the solar array system and therefore had to have its fair research. We looked at its cost particularly. When researching the battery, we had to consider storage capabilities, battery life, efficiency, and type, particularly between lithium-ion battery and lead acid. Finally, we needed to consider the battery size and its capability to handle the load produced by the panels and distribute the desired energy output to the household.
The design solution. The group's final design was decided through a work evaluation matrix based off of specific criteria that was deemed the most important. The evaluation concluded that a gable roof on a 30-degree angle would be the most efficient. This allows for maximum absorption twice a day when the panels are normal to the sun, and 85% absorption the rest of the day. A zinc roof was decided because it will decrease energy usage by 40% and will last for 100 years. The design will consist of 34 monocrystalline panels, which have a life expectancy of up to 35 years, and will have a module efficiency of about 20%. They have a high efficiency compared to other types of panels, and its optimal performance is during high heat and low light. The batteries that will be storing the energy are Sonnen Eco 10 lithium-ion batteries. The design will require 5 10-kilowatt batteries, which will fit well within the 64-meter square area. These batteries have a 100% depth of discharge and a round-trip efficiency of 90%. The batteries will be kept in a shed where they will be easily regulated and kept away from light and changing temperatures. This will allow the batteries to have a lifespan of up to 15 years.
In this section, we will discuss energy calculations used throughout the project. So firstly are the calculations used to obtain specifications of the system, such as the number of batteries, size of the system, number of panels, and the size of the controller. So the first value listed of 5,700 kilowatt hours comes from the yearly energy use of a family of 4, which was originally about 9,500 kilowatt hours, but the 40% deduction of energy from the zinc roof has been considered. The kilowatt hours used per day is then calculated and multiplied by 3 to give the 3 full days of energy use if none is generated. From this, it is then trivial to find the number of batteries needed. And after, the size of the system can be calculated with efficiency loss incorporated, allowing for us to specify the number of panels required. And lastly is the size of the controller, which is also a trivial calculation of dividing the size of the system by the battery voltage. Secondly are the energy calculations done for energy production. Once the system had been outlined, energy production over a year was analyzed, and this analysis was broken up into the different seasons to allow for more accurate financial analysis. As seen in the table, summer, spring, and fall months produce much more energy than the winter, and the goal of 5,700 kilowatt hours of yearly production was greatly exceeded. This extra 3,196 kilowatt hours of energy produced will then be sold locally and used for net metering credit to reduce energy costs in the winter months while also reducing the payback period of the system. And this slide here is just a brief overview of all the equations used in energy calculations throughout this project.
On the financial side, our team goals were to minimize the payback period of the system. To accomplish this, we calculated the capital investment required to implement the solution and then how much the system would save each year compared to traditional grid-based power in Kingston. To calculate the capital investment, we took the sum of all the components listed below and then subtracted the amount that the value of the home would increase when installed. It's estimated that the value of a home increases roughly 4% with a solar system, or around $20,000. Our final capital investment was around $29,000, quite steep. However, this includes the cost of the roof, an element that, yes, increases the initial investment. However, it decreases the amount of energy we use each year, thus decreasing the payback period of the system. Each year's savings for the system are different. However, with grid-based electricity costs rising by 0.2 cents a year, the savings increase over time. Other contributors to the annual savings come from the climate action incentive programs, not having to pay for natural gas or the steep carbon taxes, and from extra generated energy that we sell to local households. Taking into account the initial capital investment of around $29,000, our system returns a net profit 8 years after installation. This 8-year payback period allows enough profit to be generated that after 15 years, when the battery needs to be replaced, it can be paid off exclusively using funds saved by the system. After the full 30-year lifespan of the panels, the system will have saved roughly $67,000.
Finally, we have the evaluation. To start off, we have the power needs. With zinc roofing, the power usage decreases 40%, which brings annual energy down to 5,700 kilowatt hours per year. The battery system can last up to 3 days. The system overall generates nearly 9,000 kilowatt hours per year, which is then translated to net metering for winter months and is also sold to the power grid. And the solar panels have an efficiency of 20%, bringing the total score to 4.5 out of 5. For the financial evaluation, we have a $49,000 initial capital investment with a house value increase of $20,000, so a net decrease of assets of $29,000. The payback period is 8 years, with a $67,000 net return at the end of the solar panel's 30-year life cycle, and an average annual cost of $60 for maintenance, given the financials of 4 to 5. The environmental cost-benefit evaluation. With a 40% decrease in energy needs, there's also a 40% decrease in investment for the battery and solar panel system, and the system also supplies nearly 2,500 kilowatt hours of green energy every year, giving a sustainability of 4 out of 5. The zinc roofing requires no maintenance. It makes solar panel maintenance very easy. This system is entirely self-sufficient with net metering considered for winter months, and the battery can last up to 3 days of full power use, giving reliability of 5 out of 5, earning a total of 4.5 out of 5. To summarize the evaluation with all the numbers considered, the solar panel system design earns a 4.3 out of 5. In conclusion, the solar panel system design passed all aspects, achieving a final ranking of 4.3 out of 5. Therefore, Group 729G deems this project a success. Thank you for listening.